to yourselves and also present it to the students for the 2015 and beyond. So really, the University of Glasgow has been my start point, potentially the end point of my career. And I have had a lot of experience which I have built in the past 20 years that I'm now going to be bringing into the role. And for the next 40 minutes, my plan is to tell you guys the tools I've used, the tools I've developed, and the design, manufacture, assembly, and management tools which can be of great use as you enter into the real life as an engineer rather than an academic. The first tool that I would talk about is defining a customer's needs. There is too many examples of people who think, I can design the needs, I can define the needs by looking at what's in the marketplace and then designing something to compete with it. That is not a good way of defining a customer's needs. You need to use smart problem statements. You will see this time and time again, both in engineering and when you're looking at management tools and management strategy. Smart means you're smart, but it also stands for specific, measurable, achievable, relevant, and time-bound. So, a bad example of defining the user's needs is saying we need to design a new range of pumps to compete with Grundflow's aqua pump range. And I've made up those names, doesn't really exist. But simply to say I need to design a new range of pumps to compete with our competitors, that is not a good problem statement. That is not a good definition of the needs. A good example would be pump sales for the water industry in Europe have dropped by 10%, and this is due to the emergence of new low-cost competitor products. Therefore, a new pump range should be developed with the material and manufacturing cost 15% less than our current range, and the plan is to introduce that in the water industry by May 2016. A lot of words there, I realise that. It's not snappy, it doesn't roll off the tongue, but it is a fully defined, smart problem statement and desired state. The specific element is that you have lost 10% of the marketplace, and also you want to reduce the manufacturing cost by 15%. Measurable, again, the manufacturing cost of your new design has to be 15% less than the current design. Is it achievable? Basically, that's the judgment call from the organisation. Is this something we can set out to achieve? Because if it is not achievable, you're wasting time and effort. Is it relevant? Basically, we are assuming in this instance that you're a pump company and you are designing a new range of pumps. So the relevancy is saying, is what you're planning to do in keeping with the machinery, the equipment, the skills that you already have. The time-bound element, you can see quite clearly that the target is to achieve it by May 2016. So when you are working your way through the design and development process, you have all these facts, figures, and numbers that you can benchmark yourself against, and you can see as your product range becomes simplified, as you develop and introduce the new redesigned products, whether or not you are achieving the target, the goal, the ambition that you stated when you set out on this. So when you are defining the needs within the dry powder inhaler, for example, you should have the person who's doing the market research section should have it defined, saying this is what we want to do, this is how we're going to do it, it is relevant, it is achievable, and this is the time frame in which we're going to be can use it in this example, you can use it in the dry powder inhaler, and you will carry on using it through the rest of your careers. It is very relevant and very important. The next stage I'm going to be talking about is research and development. Don't worry too much about chance and retest this now, because I am able to
Can't even see it.
Oh.
One point to mention, when I looked at the notes on Moodle, it shows up the bottom half of this only. So I'll talk you through it all. You might want to make a couple of notes on it. This is what they call a stage gate process for research and development. It is a way of controlling and defining each process that you go through. I drew up a chart, and I'll be honest with you, I took most of the information from Wikipedia because it's got a brilliant section on R&D. But when I went into Dyson Power, I realised that any processes in place for research and development, and yet they were spending millions on it every year. But they had nothing defined, no committees, no way of actually saying, yes, this project is working, or this project is not working. So I set about coming up with a strategy where we look at the first stage, which is right. The first stage is coming up with a preliminary analysis and identifying market needs. Now that will probably sound quite familiar because there's people within your groups doing the market research. That's the starting point of any new product development, whether you're looking at small, large-scale manufacturing of consumer parts and off-the-shelf components, or whether you're talking about million-pound investments in machinery, either offshore or going into space. It doesn't matter. You have to have the market needs. Before you can identify the market needs, you need to do your preliminary analysis of the customer requirements. So once you've done this, there's a wee decision point you have to make. You need to either kill the project, hold the project, reiterate the project, or carry on and make your way through onto the next phase. There is questions that you should be asking yourself at each of these phases. What is the quality of the execution? I.e., how well have you done that process? Is there business rationale to continue with the process? And have you got a next stage action plan in place for moving into the project definition and scoping phase? Usually, you've not invested too much time, money, etc. in the stage gate process at this point, so it will move without too much difficulty into the project definition. You then start defining the project, who's going to do what. You look at the competitors to see what is available on the market already. Again, this is stuff you guys are doing in the dry powder inhaler project. During this phase, you're looking at the information gathered, you're analysing what you have, you produce deliverables, you produce a report. Quite often this is a report to the engineering manager, the engineering director, or even a board on the R&D committee. And you ask yourself the questions, have you done it well, have you still got a business case, and is the business case strong enough to proceed on to the next stage? And if it does, you jump down onto the next phase. If it doesn't, you either go round the loop, start again, or you just kill the whole process and concentrate on what you already have. Next step is the generation of the business case. Setting aside, doing your financial analysis, getting your costs together, working out how much spend you're going to have, who's going to do it, when they're going to do it, and what the payback time is. The business case is what you're going to present to the senior management teams, the directors, the general managers and so on. These people don't care a lot about the fine detail. They don't care about the materials you're making it from, what it looks like, how it functions. They're looking at the facts and figures, the bottom lines of the accounts. They want to make sure that the company will continue to make money when this new product comes into play, and ideally make even more money than we had, or gain a larger market share. So the business case, very important document, and this is the one where a lot of the senior managers will be reading and deciding whether you continue or not. Again, you make a decision, do you carry on to the next stage? Usually at this case it's not the individual in the R&D that's making the decision, this is the senior management team or the R&D committee or a forum of that nature. It continues and you're allowed to start going into the design, the development and the technical appraisal. So this is all the AFE analysis, this is the solid work drawings, this is the stuff that you guys are doing already. But point to note, there's a lot that an industry goes through before they actually get to that phase. So try not to be tempted to immediately launch into the design without doing the financial analysis, without doing the business case, without seeing that there is a true justification of why you should proceed with the development of this new product. The next stage, if you have gathered your design, you've produced some first stage engineering drawings to go out for pricing, etc. You've done your analysis work and you're happy to continue. Then we'll look at doing testing and validation. So this is producing prototypes, real functional prototypes, validating the design by comparing the results of the prototypes against the results of your initial calculations, doing more analysis on what you have produced, refining your design and reiterating. Usually there is a long phase of testing. I told you I was the technical manager in Diamond Power doing long retractable soup blowers. We kept a soup blower running backwards and forwards and backwards and forwards for 6 months during testing because we wanted to see whether it would experience fatigue, we wanted to see whether it would wear out, we wanted to make sure the materials were robust enough. Now, it wasn't a realistic environment because we were doing it in our workshop, our factory. In reality, the environment it's going to be operating in is going to be hot because these soup blowers work in boilers and maybe 600 degrees centigrade, maybe thousands of degrees centigrade. It is really hot, dusty, smoky environments that they're working in. So after we done our prototype testing in the workshop, we then move on to putting a product in place in one of our potential customers' facilities. So we do field testing, and the field testing is still part of the testing and validation, is more useful because it's realistic operating environment. You can't go straight to field testing without doing your in-house testing because you are potentially exposing any weaknesses in your product to a future customer. You also can't really charge a customer for a prototype that you have not yet launched to the market because nobody wants to buy the very first product that you make because you haven't proven the reliability. So field testing is a good way of getting a product into its working environment, getting data and feedback from it. Usually the sweetener, I'm not going to say we bribe the customers because you're not allowed to, but we have an agreement that if we put a prototype into place, we do not charge them for the prototype and we give them free maintenance for the other machinery that we have round about in the same facility. And that allows the customers to get something out of it. They also get a free machine, but we say to them that we might take it back to change it if we find that there's problems developing. And it allows us to put bits of important machinery into power stations, into offshore installations, into working environments and see whether it actually works. Again, very useful, but it doesn't make us any money at that point because it is not a financial, we have not sold the product. The next stage is where we have a big party, and that's the launch. We get lots of customers, potential customers in, we produce brochures, and we celebrate that we are launching a new product which will give the customer exactly what they need. Sometimes when we are developing a new product that is actually cheaper than the existing product, we may decide not to launch with a big fanfare. You understand what fanfare means? A big party. We might actually decide to launch a product quietly, because if we have cheapened the manufacturing of the product by using more cost-effective methods and more cost-effective materials, then we just want to launch into the market at a lower price than our competitors and start winning more orders. So it really depends on what your product is and what your market is, whether you launch it with a big celebration, adverts and parties and so on, or do you just slowly let it go into the market, secure orders and become a market leader because of the low cost that's involved. So that's another area which, if you do it badly and you launch too early, if you have products which have got problems with them, then your reputation could be damaged beyond repair. So very important that you pick up the timing correct for a launch, and after you have launched it, you do a full review of the process to make sure that no errors were there, that you've got the timing right, and that your product is suitable not only for the industry just now, but for the future developments that may happen within the industry. So you go full circle and do a full review and document it. As I say, that was pulled together basically a number of years ago from Wikipedia when I went into a department and realised they had no process. But you can look at various other industries and various other companies, and it's called a stage gate process, and you will see it time and time again. Very good, robust, sensible way of executing new product development. The next thing I would want to talk about is how to evaluate the existing product that you have and a customer, a competitor's product or a competitor's range of products. It's, again, as I said earlier, you should not launch a new product just because you want to compete with a competitor rather. You want to look at what's available. You have to analyse your existing product and the features that were designed into it and establish, are these key features still required in the marketplace, or were they introduced 10 or 20 years ago to accommodate a requirement which no longer exists? Industries change, customers' needs change, regulations change, and sometimes we might decide, okay, you are now allowed to introduce polymer materials or polymeric materials into machinery, which were never allowed before. You might find that there is design changes that competitors are using that you'd never thought about because you never developed it with these either methods or materials in mind. So you look at the key features of your product and say, are they still required? Can we alter them? Can we simplify them? Or can we eliminate them completely? We also look at the functional components. Are there any new alternatives available? A good example of this is the pump industry, or any industry which is pumps, compressors, rotating machinery, where they used to use packed gland sails. This is like ropes that were wound around the shaft, and the design was such that you had this rope to stop the water from coming out through the seal. Very common back 20, 30, 40, 50 years ago. They actually used to use asbestos impregnated ropes because it had very good sealing properties and heat resisting properties. That asbestos is now not allowed, and packed glands is a very difficult way of assembling a mechanical seal. So the industry has moved on. We now have mechanical seals in place. Mechanical seals are smaller, they don't take up as much space, but yet there are still designs that are available on the market where you have an allowance or a large space within your seal envelope because it was originally designed to accommodate a ideal. So we need to be able to review the designs and move with the times to ensure that we are not over-engineering to suit obsolete components or obsolete features. Material selection as well. I kind of talked about this already, but is there any cheaper materials available? We've now got hybrid materials, ceramic materials that were never available before. There's all sorts of new polymers and composites which may not have been used in a design that's 30 or 40 years old. If you go into industry and rather than designing something new from scratch, you find that you're in charge or you're working in a design team and they have got pumps, compressors, components, items, machinery that has been around for 50 years. You need to be able to review that objectively and make improvements. And this is the easiest way to go about making that. Look at materials. Sourcing as well. The past 20 years, when I originally studied mechanical design engineering here, and by the way, he was my lecturer, Green. when I was studying in here, we would buy everything locally. You didn't have this massive global village that we have now. So we would look around Glasgow, we would look around the west of Scotland to see where to get materials. These days, you could globally source materials, you've got things flying left, right, and centre. There is new, easier ways of obtaining materials, parts, and components. And this needs to be accommodated within the design. We should not design for what we have within a 5-mile radius. You need to think about it sensibly. Don't spend too much money on the delivery and the packing, but I'll get to that in a second. Ease of manufacture. I'll not talk too much about that because you've just had about an hour on ease of manufacture and ease of assembly, and ease of assembly as well. So these are the key steps to critically evaluate the designs you already have, and also to dissect and evaluate a customer's product. There's a phrase used in industry called reverse engineering, and it involves obtaining a customer's product, and that may be a small consumer bit of microphone or something, or it might actually mean spending thousands, if not millions of pounds, getting a second-hand pump or compressor, turbine, generator, stripping it down and learning how they went about it. Reverse engineering is very common. It's not fraud, because you're looking at it, you're learning, and you're seeing how to adapt improvements in the ranges. And if something has already entered the marketplace, it's freely available to buy, procure, and learn from as well. So it's something that when you're reviewing your design, if you have the ability to learn from a competitor's, then you should take advantage of that. Now, waste analysis is another part that I like to speak about. The easy way to think about waste analysis is an acronym called TIMWOOD. TIMWOOD stands for transport, inventory, motion, waiting, overproduction, overprocessing, and defects. This is also a very useful tool to use when you are looking at the process rather than the product. Okay, so the process could be the design process, it could be the manufacturing process. The way to think about it, if you look at the T from TIMWOOD, the transport, are you moving the parts a long distance? Are we buying parts from the Far East that could be bought locally or vice versa, depending on where that's manufactured? When you look at inventory, we all now recognise that manufacturing large volumes of parts and holding them in stock is not good practice for manufacturing industry. So using just in time, using the various areas, you try and keep the stock levels down to as low as possible so that you do not have capital investment money tied up in the stock. Specifically slow-moving stock as well, where you have hundreds and thousands of parts sitting on the shelves which are not used for years. Again, in the last job that I had the task of looking at this slow-moving stock list that money should be in assets of the company. They should actually be using it within the products that they were manufacturing and selling. And in some cases, we did actually adjust the design of some components to make use of the parts we had in the stores, just to bring the level of slow-moving stock down. The alternative is to scrap it, and as you all know, the scrap value for any of these metal components is only a fraction of what you pay for it when it's new. So inventory, try and keep down to as low as possible. Motion, when you're looking at waste analysis and trying to make a good, efficient manufacturing and design process, you have to look at the motion of, are you turning around, are you twisting, are you moving, are you assembling, for example, upside down, which in some cases, if you think of a car and you're fixing underneath a car and you need to have an upper half, you're doing all the work like that. This is also part of the waste analysis process, where you want to be looking at the motion, especially if it's a human being that's doing it, and saying, is there an easier way, a faster way of doing it without having to move to a position which causes difficulty. Often that involves using jigs and fixtures and investing in special tooling, where you pay the money once, but you get the benefit from it every single time it comes to doing that process. Waiting is another waste. Waiting time, when I worked in Weir's, it was famous because we would never have the parts that we needed to assemble the products at the time when we needed to assemble them. So we would get the route card, which tells you what to do, and then say, right, you need to put part A into part B, and then assemble it into part C together with DE, using these tools and these materials. You would go to the stores and find that they'd only been ordered the day before, wasn't available, and you had to go on to something instead. So waiting can be a big problem, certainly within the manufacturing industry. Overproduction, similar to inventory and stocking. If you make too many parts which you cannot actually sell, again, all the money, all the cost is tied up with these components, and you're not bringing the money back into the business, and you can't invest. Over-processing, slightly different. We call it over-engineering. In Glasgow, there is a term called Clyde Built, and it means good quality. It means having good materials, thick components, bits that are never going to wear out. In reality, in the modern workplace, though, that's considered to be over-engineering. If you have parts that are a lot thicker than they need to be, then you're spending too much money on your materials. If you have a feature which has got a tight tolerance on it, but it doesn't need to have a tight tolerance on it, then you're spending more money than you need with both the manufacturing, the machining, and the inspection process. So over-processing, polishing and painting is another example. Components which are painted that are neither exposed to the atmosphere or actually visible when you look at it. You need to think about where a part is going to be used in the assembly, which bits need good surface finishes, which bits don't need good surface finishes, which bits need painting. And as Dr. Green says, if we find you're producing engineering drawings and so on with very close, precise geometries, tolerances, and surface finishes, and there's no need for it, then you lose marks because you are over-processing, you are calling for extra activities which are not required. And then defects, this is a big one within industry. If somebody makes a mistake, either in the assembly side or the manufacturing side, then that is a very obvious recordable defect. The other bits that are less obvious is if the engineer, if the designer makes a mistake in the drawing or the bill of materials, he might call up a design which is impossible to produce. And he will not know that until it goes to the shop floor, and you get a very angry machine operator come up to your desk and say to you that it is impossible to machine this. What are you thinking of? You've got it completely wrong. And that happens to everybody. That's happened to me just about every job that I've had. You get used to it after a while. Just be polite to them. You get the drawings changed, you put something in place to make sure it doesn't happen again. But it is very important to log any defects design, the bill of materials, and of course when you're getting something manufactured. Sometimes, if they make a mistake with the manufacturing side of things, you can still carry on and build it. Even in the nuclear industry, I worked in the nuclear industry at Wears, and part of what we done was look at concession requests, where the guys on the shop floor would manufacture something, it would come out wrong against the drawing, against the tolerances and so on, and we would do the calculations based on what they have produced, and then say, is this acceptable, or does it need to be put in the bin? And, you know, 50% of the time, we can continue to use the defect product and it will not lead to failure. Sometimes we can accept the defect, but we need to change the design of other components to accommodate that product. But the important thing is it needs to be analysed and examined by the designer. It is not suitable for something to be defective and then carry on using in manufacturing. It needs to be reviewed each and every time, and that can be quite a large part of an engineer, of a design engineer's role in the company. So that gives you the full breakdown of the Tynwood waste analysis. It is a very handy tool as well. We don't often define it like this. Sometimes we just do it because a lot of it is obvious. Sometimes you need to sit in a specific team and see whether there is any processes you can improve by using the Tynwood waste analysis. This is part of what they call lean engineering. Another tool that I'd like to talk about is HAZOPs, HAZIDs, and risk assessments. It's very similar to failure mode analysis, which we do elsewhere. And basically, when you do hazard identification and also the hazard operability study, they are very similar, but the hazard identification, as it sounds, you're identifying potential hazards. The HAZOP, however, is looking at how potentially something could go wrong that affects the operability of a product, how something functions. A risk assessment, however, looks at the safety of a product. We can do a risk assessment and find if something is very likely to fail, but if it's very likely to fail in a safe manner, then it can pass through the risk assessment process. Risk assessment tends to specifically be whether you are going to hurt somebody by the product failing. And when we do our HAZOPs and HAZIDs, they are linked in with the risk assessments because we will look at the likelihood of something failing, and when we do the risk assessment, we look at whether the functioning of something is going to harm anyone, and also the way in which it might potentially fail could harm somebody. I'll talk a little bit about that in the later slide. Whenever you're doing any kinds of these hazard operability studies or risk assessments, you should really have groups of 5 or more, similar to your groups just now. It should also have multidisciplined people within the team. So we don't want 5 design engineers all sitting around, because they will identify the strengths of the design, but they might not look at the issues during operation or issues during assembly and so on. So it should be multidisciplined groups. The risk assessments should look at quantifying the likelihood of the hazard occurring, and then quantify the consequence of this hazard occurring, and give the product as a numerical score. So risk assessment equals the likelihood multiplied by the consequence. Again, the next slide will tell you a little bit more about this. And the assessment should determine the level of acceptability in terms of minimal risk, manageable risk, and unacceptable risk. So, drawing on that, this is a risk assessment. I know you won't be able to read it from here, but it's in your middle. This is one that I done in 2011, and it was based on the mechanical hazards of a large piece of rotating machinery damaging an operator. So in this example, we were looking at rotating parts, the first section, and we're saying that the harm which could be occurred to hazards from exposure to rotating parts is entanglement, drawing in, getting crushed in the machinery basically. Who might be harmed? Well, the machinery operator might be harmed. What measures have we got in place to prevent that from happening? And we said that we've got guards in place, all the moving parts are contained within the guards, and we have done non-destructive testing of all the components which are put together to make sure that all the parts used are good quality and won't fail on us. So we have quantified, in this case, the severity, the consequence of getting crushed within the moving parts or rotating parts. And of course, the severity of getting dragged into a big machine is you're going to be dead. And you're going to continue to be dead for the rest of your life because you're dead. So that scores a 5, which is the highest in the severity scale. The probability of that happening, though, because of all these measures that we've got in place, are scored 1 in each case. You multiply 1 times 5, and you get 5, and that is what they call, if you look at the scale here, 9 or less is a low risk rating, which means it's an acceptable risk. If we'd done this in a different manner, and somebody said, actually, there is a relatively high chance that you might get drawn into the machine because we don't have a guard in place, that might score a 3. In that case, it becomes 5 times 3, which gives you 15. If you look at the chart, when you get 15, it becomes a medium risk, and you have to put safety notes, warnings, and manage the risk involved. If it turns out there's actually a very high risk that somebody's going to get dragged out, and that becomes a 4 or a 5, then 5 times 5 is 25, and it just means you cannot continue with that design as it stands, so you need to completely redesign it. So, as I say, if you've got 1 times 5, you get 5, that's in a nice green area, that means you can live with these risks. If you've got 2 times 5, down there, you get 10, or 2 times 5 over here, you get 10. So if the risk and the consequence gives you a value of between 6 and 10, then that means you have to put special precautions in place. That could also mean putting more instrumentation in the design. You guys doing control systems just now? Have you done that back in Singapore? Yes? No? Yes? Well, the control systems, you can put more control systems in place to predict and protect the operator in the event of failure. And that allows you to still be within the manageable risk. It's only when you get into the red region that you want to look at completely redesigning the product. So, to conclude the risk assessment section, you've got low risks, that means no further action, medium risks, warnings, labels, guards, etc. High risks, you just cannot live with high risks, they need to be redesigned. The last section I want to talk about is the measures that we monitor when I was running the design office. The best way to keep track of performance of a design office is to look at it in terms of quality, cost, and improve. Performance can be measured in terms of has the product you've designed meet the speed, pressure, temperature, power, the actual physical characteristics that you need to be designing. Has the product met the specified demand? And you find that out through testing and also when things are getting commissioned. The cost you measure in terms of both the engineering time that you've spent coming up with the design, generating the drawings and pulling together the bill of materials, and also the actual specific costs of the materials that you specified when they've pulled it all together and assembled the component, assembled the machinery. And then finally, well, engineering and labour, as I've already talked about, you've got the sales issue. Once we have designed and sold the product, are we getting the sales in? Are we actually making money from selling the products to recoup any of the costs that we have spent developing in the first place? So, looking a little bit into the quality, as I say, the best measures in every company, in every industry, you look at quality, cost, and delivery. Quality here, you're not going to be able to read it accurately, but this is a real sheet that I used when I was down in Power to keep track of how many times we had to change bill of materials after issuing it to the shop floor. So there's a usual problem when you're working in the industry that people are screaming out to get their instructions to find out which components to buy and start buying them. So you release the first draft of the bill of materials, and then you may have to change it as a design develops, and you have to incorporate some additional requirements. So that means you have to reissue it to the shop floor. Again, nobody is happy when this happens. We have very angry fitters coming up, or potentially making mistakes because they've used old copies of the documentation instead of the current copies. So I would keep track on a weekly basis of how many times, and also on a monthly basis, how many times we would need to have changed our bill of materials after releasing it to the shop floor. I would also look at the reasons, because sometimes the reason is actually because our customer has changed what he has ordered. When you're working in a large engineering company, the customer is a very tricky character, and he may be always right, but he is always very tricky, very difficult, because he can change and then change and change again. So when a customer changes his requirements, we have to change our designs and reissue the instructions to the shop floor. Can be very difficult, but we need to be able to control it and ensure that we are not doing too many changes while we still meet our customer requirements. Again, this is another unreadable one, but just to tell you what it is, here we have a breakdown of all the activities that go into producing a turbo blower. So this is the drawings that need to be created. It's unreadable because I don't want you going away and copying it, because you'll start making your own turbo blowers. But in one column you have the amount of components in the assembly, which is very similar to what Dr. Green was showing you a wee while ago. And then the other columns is the amount of time it takes to produce these drawings. And if you have more than, if you are selling a batch of 20 components in the one run, then you would only produce the drawings once, which makes it more efficient because we're not constantly repeating engineering drawings and reissuing instructions. The testing, however, does need to be done 20 times, because if we've completed a component and there's a large engineering element to it, then the customer will specify the amount of testing he needs to see on it. What we see on the right, which is a bit more readable, is the graphs that I produced on how much engineering hours I thought it would take for each activity, which is actually the dotted lines, and the reality of how many engineering hours it took to do the project, which is the solid line. So on this graph, it's a little bit confusing, but there's different colours to represent the projects that we were making at the time. At the snapshot, which was Christmas 2011 probably, we had 4 or 5 projects on the go. This one shown in blue was the closest to being completed. We projected there was going to be a lot of hours taken in at the end of the project as it went into testing. As it happened, we didn't test that until the following year, so it would have continued up. But this is a good graph where at the start of a project, we not only estimate how many hours it's going to take for the engineers to do their job, but we plot which week they're going to be doing each hours, and you get a signature of the profile of the engineering spend during a project. And then as the weeks go on and we've got real life figures from timesheets, we start checking the amount spent against the projected spend on that project. And as a manager, it was important to me to make sure when we overspent, such as here, we knew exactly what we had done that caused us to overspend. And that project, Saturday overspent. We ended up spending twice as many engineering hours on it compared to the time that was allocated to it before. And the reason for that was the sales team aggressively sold it with a small amount of, a small allowance for the engineering work, which actually wasn't possible to do the engineering work in time. And we knew that. We still aimed for the budget that we had, but we never met it. Fortunately, we did meet it with various other jobs that year, and it wasn't as big an issue, but it is very important for managers to be able to see where we were overspending. The last one from this lot is the delivery. So as I say, you get quality, cost, and delivery. Quality was the defects, the cost is the amount of hours and the price. This is the delivery. When we say we're going to produce a drawing and the dates that it needs to be done, I use conditional formatting to see project types. These are the project numbers going along the side, and then the activities and the actual deliverables going down on the vertical axis. Using conditional formatting, I can see, I could put in dates of when we expect a drawing to be issued, and then when the date the drawing is issued, we finish, we populate the box. It then does a comparison and tells you whether you're on time and gives you a green box, whether you completed it late, gives you a brown box. If you've still got time to do it, it gives you a yellow box. And if you are overdue, you haven't completed the documents, the drawings. Again, with your dry cleaning and nail, an example of this can be getting the CAD work done in time to do the mold design or the solid model. So we would look at the requirements, and if it was late, it would be a red box. Now, you don't need to be able to see the actual numbers in the boxes to see at a glance that there's a problem with that job and problems in that activity. So this is important for a manager within an engineering office to be able to see at a glance, just by looking at the colours, whether we are doing well or whether there is difficulties. In that case, I could see there was difficulties because there's red all over it. That means drawings haven't been produced, and the reason for that was we had lost a member of our team. We only had 6 people in the team, and we lost one of them, which gave us 5, and we had nobody there to complete the drawings on time. So I understood what was required, and I understood what was what I needed to do to rectify the situation, which was recruit another draftsman, strengthen up the team, and manage through the difficult process. Again, it's very important to be able to visually see that without having to dig into the details every time, and it will also allow me to prioritise which of the projects we assign people to, because you can see at a glance the ones that have got difficulty and the ones that are going well. So, to summarise the past 40 odd minutes, I've talked about using SMART objectives. Don't know if you all remember what the SMART stood for. The specific, measurable, achievable, realistic, and time-bound, I think. Check back the notes to make sure that that's right. Eliminate, identify waste. Can anyone remember the name that I used for the waste analysis?
Tim Wood.
Yeah, it was Tim Wood. Tim Wood waste analysis. Identify and eliminate risk using the risk assessment, HAZOPs and HAZIDs. Map and plan the design process using the stage gate, and then monitor quality, cost and delivery throughout the entire process, and make changes as required. So, that's it from me. Does anybody have any questions?